Welcome to the third part of week 7 of the class Neuronal Dynamics. We have seen that adaptation together with an exponential integrated fire model can account for a variety of firing patterns, in particular for adaptation. Now let's move on and change the formulation a little bit. Let's focus for the moment on the exponential integrated fire model. It has this linear term that was mentioned before and the exponential term. This exponential term is characterized by a parameter delta. Delta controls the rapidity or the sharpness of the kink, the sharpness of the bend down here. So you see here a zoom in this small region here with different values of this parameter delta. Now, this is a parameter of the model. If you measure the curve, the nonlinearity of the exponential integrated fire, and you fit with this linear plus exponential term, you find a delta in the range of 2 millivolt. That's not a lot. That means it's really a sharp transition up here. Now let's consider what it means, a sharp transition. But let's make it sharper and sharper. If it's really sharp, then it's like saying the threshold sits right here, where the kink is, where the curve bends upwards. Thus, the exponential term for very sharp delta can be replaced by just a sharp threshold. And that means we are back to the leaky integrated fire model. Now, we said earlier this week that an exponential integrated fire model is fine, but you need to add adaptation variables. And the same holds for the leaky integrated fire model. Just add some adaptation currents, WK, maybe 5 different adaptation currents, and each adaptation current, WK, is controlled by the linear differential equation that we have seen before, where this parameter BK controls the jump size at the moment of the reset. The voltage itself is reset to UR. So it's just like in our discussion of the adaptive exponential integrated fire model, except that the nonlinear term here has disappeared, and instead we work with a sharp threshold. The threshold itself can be time dependent as before. Now let's look what this gives. I now have two coupled linear differential equations. If I know the jump size, if I know the moments of a spike, if I know the firing times, then this is just a sequence of short current pulses in a linear differential equation. But we have seen in week 1 that such a differential equation can be integrated. And then we have our expression for WK. An explicit expression for WK, which we can insert over here. The result is that the reset that's happening after each spike can be integrated up. First I integrate up the W equation, then I insert it in here. This is again a linear differential equation which I can integrate. And the result of the sequence of two integrations gives the effect of the spike that has happened in the past at time TF. Similarly, if we start with the input here, the input goes in this linear differential equation, and we know how to integrate such a differential equation. And the result is this term here. Note that the integration can be done despite the fact that there is a coupling between the voltage and the W variable. as long as it's a linear differential equation, several coupled linear differential equations, driven by spikes, driven also by the external input. As long as this is the case, we can do the integration. Moreover, we still have the dynamic threshold. The dynamic threshold means that after each spike, the value of the threshold is higher than it would normally be. And this integral formulation has been called the spike response model. Why this name? Well, this is a spike, and the response of the spike, its own spiking, of the neuron's own spiking, is this refractory and adaptation kernel eta. Similarly, in a network, the input current would consist of spike arrival. Integrating this out means that this kernel kappa describes the response to spike arrival. Now let's see how this model works. I apply some arbitrary input to some neuron. In the case of my model neuron, this means I filter this arbitrary input kappa, that's this first term, and if I do this starting from this initial condition, then the voltage will follow some trajectory, which I can calculate. That's this term here. And then at this point here, it hits the threshold. At the moment of the threshold crossing, we paste in the shape of the spike and, importantly, this spike after potential, which accounts for refractoriness. We add over several past spikes, T prime or TF. These are the past firing times of this neuron. We add over the effects of several firing times in the past, so that this term eta, which can be very long, will also account for adaptation. And then after the spike, the threshold is increased. We have a dynamic threshold. So this is the essence of the spike response model. And note that even though we have come from the integration of the leaky integrated firing model with adaptation, in the end, these kernels of filters here can be chosen completely arbitrarily in a way that they would best fit experimental data. And there are three of these kernels. A filter for the external input, a filter that describes refractoriness and adaptation, and a filter that accounts for the dynamic threshold, an increased threshold immediately after a spike. Suppose I take such a model and I take a kernel eta, the refractor, the spike and refractoriness kernel, which has first the spike, then it has a downswing, important for refractoriness, and then it has a second bump and a much longer second downswing. And then I take a neuron and I assume that I inject a step current. And the result of this step current integration is that we first integrate up to a threshold, that's this part here, and then we have a first spike. We paste in that spike. Immediately afterwards, firing is impossible. But then the membrane potential increases again. So we have a second spike, we have a third spike, a fourth spike, a fifth spike. And this burst of spikes stops only because the sum effect of all these negative contributions, the hyperpolarizing spike after potentials, will finally turn firing off. And then it recovers. In the end, we have a sequence of bursts. We have constructed a bursting neuron model by an appropriate choice of this kernel eta here. The spike response model can be described as a sequence of filters. Input is filtered with the filter kappa, comes here. This leads to an integration towards the threshold. If the threshold is crossed, we have a spike train in the output. And this spike train causes two different effects. It contributes to a spike after potential that shapes adaptation and refractoriness. And it also contributes to an increase in the threshold that again shapes adaptation. Now, let me work a little bit on this potential equation. I said this is the filter eta here that gives the feedback of an output spike onto the dynamics of this neuron, the very same neuron. Now, let's rewrite this term in a slightly more complicated fashion. I write it as eta of S delta T minus Tf minus S. T prime are the firing times, and the sum of all these different firing times. Sum over F integral ds. Now, I admit that after these manipulations, this expression looks much more complicated than it was before. Let's just check that it gives the right result. So I have here the Dirac delta function. I will integrate over S. Thus, the argument after the integration, T minus Tf minus S, that means whatever is not S, that is T minus Tf, has to be inserted where we had the S before. And so we are back to this term here. So the two expressions are completely equivalent. Now the advantage of writing it this way is that this really is the spike train. This is my spike train S of t. What is S of t? S of t is the sum over all spikes, over all spike events. So let me write this up in a more concise form. I can write this as integral eta of S, S of t minus S ds. And the integral goes from 0 to infinity. The integral goes over the past spike train. And now this term is suddenly very similar to the way we treat the input. And then I always have the u rest. So the input is filtered with a filter kappa. The output, S, is the output spike train. The output is filtered with a different filter, eta. And this is then combined with the threshold equation, which has this form here. Again, it's a sum over all firing times. And analogously to the argument I made here, I can write this as theta 0 plus integral theta 1 of S spike train of the neuron in the past, and I integrate over the past. So the three filters, the filter eta here, the filter kappa here, the filter eta here, the filter theta 1 here, all are treated in a parallel fashion. These filters are used in convolutions. Convolutions of the input with the filter kappa, convolution of the output spike train with the filter eta, and with the filter theta 1. Let me summarize what we have seen. The spike response model can be interpreted in two different ways. First, we can start from a leaky integrated fire model with an arbitrary number of adaptation variables. If the adaptation and the leaky integrated fire have both linear equation, it can be integrated and we arrive at some kernels or filters. Alternatively, we can just start with these kernels or filters and state that there are three different filters. A filter kappa, convolved with the input, and two filters that are convolved with the output. A filter theta 1 for the threshold, and a filter ADA for the subthreshold membrane potential after a spike. And these output filters contribute to refractoriness and adaptation. Now, the model is still deterministic, and in the next lecture I will add noise.